Hi, this is James, and in this video I will present some notes on Gauss-Legendre quadrature. I will develop the essential theorems and then a brief program. The level of mathematical sophistication is intended to be roughly calculus 2. To approximate the integral of some function f of x over the finite interval from a to b, we may evaluate the function at some sample points. There's the functional values at the sample points, and estimate the mean value of the function over the interval as the arithmetic mean of these functional values. This leads us to an approximation of the integral. More generally, we could have used a weighted mean of the functional values and defined the quadrature formula as the sum as k equals 1 to n of, where n is the order of the formula, of the functional values at the sample points are nodes, xk times the weights wk. The highest degree of polynomial, for which the quadrature formula is always exact, is called the degree of the formula. If the degree is at least as big as the order minus 1, the formula is interpolatory. So I'm going to let pi n of x be the monic polynomial of degree n with the n nodes as zeros. Then the given integral will be evaluated exactly by an interpolatory quadrature formula. The integrand is 0 at all nodes except xk, and we can use L'Hopital's rule to evaluate it there. Multiply by wk in sum to get a simple formula for the weight wk. If we insert this value into the quadrature formula for a general function f of x and reverse the order of integration and summation, we see that the formula is the same as would be obtained by integrating the unique polynomial of degree at most n minus 1 that goes through the n sample points. Given a quadrature formula of degree n, we can write out the Taylor polynomial of degree n and the Lagrange form for the error, assuming that the function f of x has continuous n plus first derivative. Computing the error in the quadrature formula, the Taylor polynomial cancels out and leaves the error terms with the n plus first derivative in them. It should not be surprising that we can demonstrate an error bound that contains a number depending only on the quadrature formula and the supremum of absolute value of fn plus 1 of x over the interval of integration. Given another finite interval of integration from now c to d, we can map it to the interval from a to b via this change of variables, resulting in this generalization of the original quadrature formula. The corresponding error bound gets multiplied by the interval width ratio to the n plus second power. If we were to divide the original interval of integration into k subintervals of equal length, it would decrease the error bound by a factor of k to the n plus 1. So for example, if the degree of the formula were 5 and the number of subintervals 10, it would decrease it by a factor of 1,000,000. Now, we know that we can't have the degree of the formula be twice its order, because in that case we could define this pi n star of x, and now if we do the integral over the interval of absolute pi n of x squared dx, that has to be positive. But the quadrature formula says it's 0. The quadrature formula of degree exactly 2n minus 1 is called Gaussian. We will see immediately that Gaussian quadratures imply orthogonal polynomials, so we will explain what they are and their properties. Given any polynomial of degree at most n minus 1 and a Gaussian quadrature formula, we can see that this integral must be 0. For the remainder of this discussion, we will assume without loss of generality that the interval of integration is from minus 1 to 1. Two functions are orthogonal if their integral from minus 1 to 1 of their product is 0. Then we have said up here that pi n of x is orthogonal to all polynomials of lesser degree. Such a polynomial is called an orthogonal polynomial. We can see by mathematical induction that there is a orthogonal polynomial for every degree n. This is the Gram-Schmidt process, of course. If there were another monic polynomial of degree n, say rho n of x, then that were an orthogonal polynomial, then pi n star of x minus rho n star of x would be of degree at most n minus 1. And then the integral of absolute pi n of x minus rho n of x squared is going to be 0 because this part is orthogonal to these two little guys. That implies that pi n of x minus rho n of x is identically 0, so pi n of x is rho n of x. The next integral is 0 by orthogonality, and if we multiply it and divide there by x minus xk and separate it out into real and imaginary parts, the imaginary part has an integral which is necessarily positive, so the other factor in the imaginary part of xk must be 0. The real part has an integrand with one factor which again is never negative times x minus real part of xk. And that means x minus real part of xk must change sign in the interval, or else the integral couldn't end up being 0. So that tells us that the root xk must lie in the interval of integration. Lastly, the roots have to be simple, because if a root of pi n of x were not simple, we could divide by x minus xk squared and integrate with pi n of x dx from minus 1 to 1, and it'd be 0 by orthogonality. Whereas we can see that just rewriting it a little bit, it's in fact positive. So the orthogonal polynomial pi n of x exists, it's unique, and its roots are real and simple and lie in the interval of integration. Now I'm going to start with any f of x of degree at most 2n minus 1, a polynomial of degree at most 2n minus 1, and I'm going to divide by pi n of x to get a quotient and a remainder polynomial. Then, in the integral from f of x dx from minus 1 to 1, the quotient remainder polynomial part is just 0 by orthogonality, and we know that since it's Gaussian, that implies that it's interpolatory, so we have a unique set of weights that makes it exact for polynomials of degree at most n minus 1. Then we can go back here and add qn minus 1 of x k to pi plus pi times pi n of xk to rn plus 1 of xk, because pi n of xk was already 0. And that means what we've gone back full circle to having the sum is k equals 1 to n of wk fk. So we've shown that having a orthogonal polynomial does in fact imply a unique Gaussian quadrature formula of degree of order n. and a degree obviously 2n minus 1. The formula we derived for the weights wk requires n integrals to find them. Instead, I start with this integral. Like mu Edelfelt, I need to use equations of integral calculus to prove all my theorems. Since the integrand is of degree 2n minus 2, the Gaussian formula is exact, and we get this result. On the other hand, we can add and subtract pi n minus 1 of x to pi n of x over x minus xk, and the difference part is orthogonal to pi n minus 1 of x, so all we're left with is pi n minus 1 of x times that pi n minus 1 of x, and that means that the only integral we actually needed to do was the normalization integral for pi n minus 1 of x. The orthogonal polynomials are called Legendre polynomials, and we will show some of their properties. There's an explicit formula for Legendre polynomials called the Rodriguez formula. P naught of x through P5 of x are plotted here in figure 2. For n, at least as big as m, I'm going to compute the integral of Pn of x, Pm of x, dx from minus 1 to 1. So we substitute the Rodriguez formula for Pn of x, and then integrate by parts once, and then n minus 1 more times. And since the stuff in square brackets is 0, if n is greater than m, then Pn of x is an orthogonal polynomial, just like it was supposed to be. On the other hand, if n is equal to m, we're going to need with stuff in the square brackets, and it's easy to show that that nth derivative of Pn of x is just this stuff. And we're going to plug that in for the square bracket stuff and do the integral. So I'm going to integrate by parts once, and then n minus 1 more times, and now we have an integral we can evaluate by the fundamental theorem of calculus to get the normalization integral of Pn of x. We can compile a couple of lines, we can show in a couple of lines that Pn of x has definite parity. To find Pn of 1, we start with the Rodriguez formula factored like this, and then apply the Leibniz rule for differentiating a product, and eventually conclude that Pn of 1 is 1. By the definite parity, Pn of minus 1 is minus 1 to the n. Now, if we compare nth derivatives of Pn of x and pi n of x, knowing that by uniqueness Pn of x is just a multiple of pi n of x, we see that the multiple is this stuff. We will require 3 recurrence relations in our program to compute Gauss-Legendre quadrature formulas. So the first one, I take x Pn of x, and it's a polynomial of degree n plus 1, so we can write it as a linear combination of Legendre polynomials of degree 0 through n plus 1. Choose any m less than n minus 1, and multiply the equation above by Pm of x and integrate from minus 1 to 1. On the left, we get 0 by orthogonality, and on the right, the only term with Pm of x, only the term with Pm of x survives, so this projects out its coefficient, a sub m. That's called Fourier's trick. Thus, all coefficients except for the top 3 are 0, and we only have to evaluate them to complete the expansion. we can compare leading coefficients on both sides, and then evaluate both sides when x equals 1 and when x equals minus 1 to get three equations for these three unknowns. Solving, we have the recurrence relation here for the Legendre polynomials. This allows us to work our way up to Pn of x, starting with P naught of x is 1 and P1 of x is x, in a way that is much less susceptible to round-off error than writing out the Legendre polynomials longhand and evaluating them directly. I'm going to get another polynomial of degree at most n plus 1 and expand it in terms of Legendre polynomials. If m is less than n minus 1, I'm going to multiply by Pm of x and integrate from minus 1 to 1 on both sides. On the right-hand side, after integrating by parts once, I see that it's 0. And on the left, I meant on the left. We get 0, and on the right, it picks out the coefficient of Pm of x again by Fourier's trick. So this is absol, but the three highest order terms, and so that's what our expression looks like so far, and we can evaluate them by comparing leading coefficients, evaluate both sides when x is 1 and x is minus 1, and solve, and we get this as our result. That's the recurrence relation for Pn prime of x. So the last relation of this section starts with this polynomial. Now it's of degree exactly n. We're going to expand it in Legendre polynomials, choose m less than just n this time, and integrate on both sides. After integrating by parts on the left once and then twice, we get 0, and on the right, Fourier's trick has just picked out the coefficient of Pm of x in our expansion. This time only the highest order term survives, and we can find its coefficient by comparing the leading coefficient on both sides. The resulting equation is called Legendre's differential equation, usually written out like this. An approximate solution to Legendre's differential equation will lead to an approximation for the roots of Pn of x. We will start with the WKB approximation, which factors a complex solution into an amplitude factor, a of x, where a of x is a real function of x and is never 0, and a phase function, e to the I phi of x, where phi of x is a real function of x. Since Legendre's differential equation is a linear homogeneous equation with real coefficients, both the real and imaginary parts of any complex solution here will be real solutions to the original differential equation. Differentiating and inserting into Legendre's differential equation, we get this stuff. Then I'm going to multiply by e to the minus I phi of x and take the real and imaginary parts, which both must be 0. As a first approximation, we let a of x just be a constant. Then the real equation up here simplifies down to just this, where we have completed the square now and forgotten about the minus 1/4 in the numerator, which is okay because we only want an approximation anyway. We can integrate that now to get phi of x is this. And note that our choice of constant of integration makes phi of x an odd function. We're going to need that later. For even n, pi n of x is an even function of x, and we know that the real part of e to the I phi of x is cosine phi of x, and an even function of an odd function is an even function. So this will be our solution that is applicable for even Legendre polynomials. And now a little bit of simplification gets us to here, and we know that if cosine theta is 0, then theta is an integer plus a half times pi. Solving that now for x, we get, if big K is n minus little k, this expression for xk. Using big K as n minus little k means that as little k increases, the xk's increase too. For now, p2m of tm plus 1 of x, that's an odd function of x, and we know that the imaginary part of e to the I phi of x is sine phi of x, and an odd function of an odd function is an odd function. So this is the solution that's applicable for odd Legendre polynomials. I'm going to work that through a little bit, and then we know if sine theta is 0, theta must again be an integer multiple of pi. I'm going to solve for x, and then let k, big K is n minus little k again, and so if we compare the solutions that we had for even n and for odd n, we see we get the same approximate roots. Now in figure 3, I'm just going to point out that if we look at the unit semicircle and take equal steps around that semicircle, steps of equal arc length I should say, except that the first step is 3/4 of a step, and the last step is also 3/4 of a step. Project those points on the unit semicircle down to the x-axis. That's our approximation to the roots of the Legendre polynomial. Now, for the Chebyshev polynomials of the first kind, you get the same picture except the first step is only half a full step, and the roots are actually exact. Similarly, for Chebyshev polynomials of the second kind, the first step is a full step, and the roots are exact again. So it kind of makes sense that since the Legendre polynomials, in a sense, lie halfway between the Chebyshev polynomials of the first and second kinds, that this taking the 3/4 of a step here would make would give us a reasonable approximation of the roots of the Legendre polynomials. So if we wanted to be a little bit more quantitatively, we could, for the first few values of n, we could plot the error in the first root divided by the distance between the first and the second roots, and we see that it is less than 1%, and seems to be approaching a limit. It would take us way out of the scope of this discussion to explain what the limit is. For a pure sine wave, you only need to be within 37.1% of the distance from the nearest root to the next nearest root for the Newton-Raphson method to converge to the nearest root every time. Okay. Now we have all the math necessary to write a little program to perform Gauss-Legendre quadrature. We have already developed our initial approximation to the roots. We have recursive relations for Pn of x and Pn prime of x. So we can apply the Newton-Raphson method to refine these roots to within machine accuracy. Then we can apply our formula for the weights, and of course we must express the monic polynomials in terms of Legendre polynomials, and then we can use the normalization integral of the Legendre polynomial Pn minus 1 of x and simplify to this. All right. Now the function Legendre uses the recursive relation here for the Legendre polynomials to get P1 of x through Pn of x starting from P0 of x, and returns both Pn of x and Pn minus 1 of x. The outer loop of our formula g of our function g formula uses our approximation to the kth root and then enters the Newton-Raphson loop. There, it invokes that Legendre function to get Pn of x and Pn minus 1 of x, and uses the second recurrence relation to get Pn prime of x. Now we can compute the Newton-Raphson error estimate and update the root. When the error is small enough, we can kick out of the loop and then get Pn minus 1 of xk and then Pn prime of xk, so that we can compute the kth weight. Now the function Gauss-Q takes a function handle f, the limits of integration a and b, and the order of the formula to be applied, and then uses G formula to get the knowns and weights appropriate for an interval from -1 to 1. Then it uses that mapping, the transformation we showed earlier, to perform the integral from a to b by a Gaussian quadrature. The script testgauss.m sets a function handle for log x times log 2 minus x. And this is MATLAB, so log means natural log. Where were we? Oh yeah, there we go. So here's my function, log x log 2 minus x, and I wanted to integrate from 0 to 2, and I choose 100 points Gauss quadrature, and it produces this approximation. If you work out the exact value of the integral by hand, or just use Wolfram alpha, we get this value. And we can see that our error is about 2 times 10 to the minus 4. At this point, I would like to thank you for your kind attention to my lecture. I hope to produce more videos in the not too distant future. In the interim, please try to think quantitatively and creatively.